This is a video solution set to exam 3 from the fall of 2011 in probability and statistics. We can use this to study this material. This material is over continuous distributions and sampling distributions. So the first question here is about a CDF. So let's we're given a formula, so we can put this in and graph that. So 1 divided by parentheses around the denominator, 1 plus 3 e to the power negative 0.08 x, close the power, close the denominator. Now, where is this? It doesn't give us any indication here, so this probably goes from negative infinity to infinity. Let's start by, let's graph it from negative 10 to 10. And a CDF, cumulative density function, should start at 0 and end at 1. So we should start at 0 and go up to 1. Well, actually, and then maybe mark it off and say 0.1s. I think I want to go a little bit lower than 0 just because I may do some calculations and want to show that at the bottom of the screen. So let's start at negative 0.1, for example. And so this negative 0.1 to positive 0.1 is just about always what you're going to want to get, or something very similar to that, for the y values for the window for a CDF. Let's graph that and see what it looks like. We may need to change our window. We should see it starting at 0 and going up to 1. We're not all the way quite to 0, and we're certainly not all the way up to 1. So we need to widen our window out. Let's go from negative 50 to 50, and maybe mark that off in 5s on the x-axis. And let's see what that looks like. Okay, there it looks like it's starting at 0, and we maybe haven't quite leveled off to 1 yet, but we're getting close. So the left looks okay. Let's bring the right out a little bit further. How about to 80? And we should see this kind of a shape. Yeah, that's the kind of shape that you expect to see for a CDF. Starting at 0, kind of coming up, and then leveling out at 1. Now, what's the probability that x is less than 7? Well, that's a y value on this curve if we know the x value is 7. So actually all we have to do here is trace and type in 7, and that will take us to the point where x is 7, and it will show us y, and y is actually the probability, the cumulative probability. That's what this is called, a cumulative density function. That's why it's called that. So this is a cumulative probability, the probability that x is less than 7. And of course it doesn't make any difference if you say x is less than 7 or x is less than or equal to 7, because the probability of actually x equals 7 is 0 on a continuous distribution. So anyway, we get the probability we want, and we want to round to 4 decimal places. 0.368. Whoops. Hit the wrong button there. Let's try that again. 3685. There we go. Between 2 and 8. Well, if we just figure this out at 8 and 2 and then subtract, we will get it, because when we do the CDF at 8, the y value at 8, that will be the probability up to 8, and then that includes the probability up to 2, so we have to subtract that. So we can do another couple of traces here. We'll trace this with 8 for our input, and we're interested in our y. So notice how I'll do this. I'm going to quit and type y, and we have that. And since this is going to change y, I'm going to store that somewhere. I'll just use a. So that's our first probability. That's the probability that x is less than or equal to 8, or less than 8. Now from that we want to subtract the probability that x is less than 2. So we can go back to the graph, do a trace, and then plug in 2 this time, and we get that y value. So notice if I quit and I do y now, that's the new y value, and what we want is our a value minus our new y value is what we want for the probability, which is just subtracting those two. And so rounded to 4 places, that's 0.1061. find the 59th percentile. Okay, the 59th percentile, what we're doing is we want the y value to be 59. In other words, we want an x value so that 59% or 0.59 is the probability that x is less than or equal to that. So we want to find a y. We've got the y value. We want to find a x. Anytime you have a graph of anything, and when you know the y value is 0.59, we can graph that, which is a horizontal line, and we want to see where those two graphs cross. So we can just do a calc intersect, which is number 5 here. It'll ask us for the first curve, hit enter, second curve, enter. Give it a pretty close guess if you can to where they cross, and there calculates the intersection. Of course, y is 0.59, and the x value there is what we're looking at. And again, it says 4 decimal places, so that's 18.2822. Alright, next problem. So that's how we use a CDF. Now the next one is a triangular distribution. Okay. And our triangular distribution, so x is triangular, 9, 15, 15. We might graph this in a minute on the computer, but what this means is when you go up to 9, below that, the probability the PDF is 0. And when you go up to 15, anything above that, it's 0. There's 15. And this one says the mode is at 15, so at 15 here it's the highest, and in between it goes straight up, so it makes a triangle. If this had been something in between, it would have gone, like for example, if it had been 9, 10, and 15, we would have 9, and then at 10 would be the highest, and then 15 here, and it would look like this. So we get a nice triangle either way. Okay, so let me just erase that one because that's not really what we have this time. Okay, so the one up here is what we have, and of course this is the x-axis right here. Y-axis is, over here somewhere. Okay, so the first thing we need to know is this total area here is an area of 1. So let's first of all figure out the base is 15 minus 9, which is 6. And here's our height, h. And we know that the area is 1/2, I'll use big B, base times height. And the base is 6 times the height. But we know that total area is 1. So 3 times the height is 1. The height is 1/3. Which means this is the point 15, 1/3. Now, let's also look at this line. So this is a line. We can come up with the equation for that. Okay. Well, let's see. It's a line. It's y equals m times x minus x sub 0. This is the x-intercept or factored version of the line. We know the x-intercept is 9, 0. So this is 9 for x sub 0. And the m is the slope. Remember, the slope is delta y over delta x. That is the change in y's over the changes in x. So notice we're going to the right 6. So that's 6 here. And we're going up 1/3. So that's 1/18. Okay, so this is 1/18 there. And so that's the formula. So the PDF formula as a function of x is 1/18 times x minus 9, and this works for x's between 9 and 15, and it's 0 otherwise. Okay, now that's useful, or might be useful later on, because that'll allow us, if we're given an x value here, that'll tell us a height at a particular x value there. We may need that in a little bit. Okay, so we want to know the probability that x is between 11 and 12. I don't know if I've got these drawn in exactly the right places, but somewhere we have an area that looks like this. It's actually a right trapezoid between 11 and 12. Okay, so what we're going to do is I'm going to make a big triangle going to here. Let's do this. So The big triangle goes like this. Okay, and then we're going to subtract off the little triangle there. Okay, so the probability that we're looking at. Okay, so the probability that 11 is less than x is less than 12. Okay, is the probability of the big triangle here, which has a base of what? Well, 12 minus 9. You got 1/2 base times the height. Well, the height of that triangle is here, which is just this PDF evaluated at the end 12. So it's 1/18. 12 minus 9. Okay, 12 minus 9 is 3. So it's 1/2. The base is 3. And this is 3/18, or that reduces to 1/6 for the height. And you work all that out. Let's see, I believe that's 1/4 or 0.25. Okay. Now, let me show you alternative method, or check. So I'm going to go back to my calculator. I'm going to clear these out, or just go down to a different one if we want to. And let's graph the formula. 1/18, formula for the PDF, x minus 9. Now remember, this only really applies between 9 and 15. So I'm going to set my window to only go from 9 to 15. And we should see a nice little slanted line like this. Okay, and maybe we'll mark that off every one. And we know that it only goes up to 1/3, so I don't have to go this high. Let me just say go up to 0.4. And let's see what kind of graph we turn up with there. Okay, so a nice little line like that. And remember, we can shade and compute areas here by doing a calc. And let's just check something here real fast. Let's do number 7, which is our area calculator. And we want to go from 9 to 15, and we should get, so lower limit 9, enter, we should get 1 for this. The upper limit is 15. It should shade the full triangle and get an area of 1. Okay, that's a good check, because that means that we probably got our formula in right. Okay, so we double check our formula. Now we can go to draw and clear that off. So clear off the shading. Next we want to go from 11 to 12, and we'll get it to shade it and compute an area this way. So we do it the same way. We can go to calc, so that's second trace. Again, number 7 is our area calculator. And we want to do that from 11 to 12. So 11 for lower limit, 12 for the upper limit, and it's going to shade that and compute it 0.138 repeating. Uh-oh, something's wrong here. 0.138 repeating. So I think I must have made a mistake here. Let's see if we can figure out where it is. Trying to do these too fast in my head here. So, oh, sorry, I know exactly what we did. We figured the area of the big triangle. We still got to subtract the little triangle. So the 1/4 is good. We still got to subtract the little triangle. So let's keep going here. Now the little triangle goes from 9 to 11. So it's still 1/2 of the base is 9 minus 11, which is 2. So that part's 1. And then we want to multiply by the height, which is 1/18. This time 11 minus 9 again is 2, so this is 2/18, which is 1/9, and this all is 1/9. So 1/4 minus 1/9, we could get a common denominator there of 9 over 36 minus 4 over 36 is 5 over 36, and see if 5 over 36, yeah, same thing, 0.138 repeating. So correct. We have to. So what we did is we found the big triangle here, and then we want to subtract the little triangle. I got in too big a hurry to show you the calculator part to finish that. Okay, so there we go. And so either way, we get the same probability, and that we did it 2 different methods. So that was a nice little check for us. So we're very confident about this. And we want to round to 4 decimal places. 1, 3, 8, 9. Now, how do we find the mean of the distribution? Well, in general, if we have a PDF and we want to find the mean, we can do it this way. We can go to that area calculator again, which is math. It's actually number 9, I believe. So, math 9. And we go to here, and we put in the function. Now, we've already got it in, so I'm just going to do it this way. Variables, y variables, function, y1. Or I can type in the formula. Then it's always x. And then, just to check, of course, if we went from, again, if we went all the way from 9 to 15, we get the full area, which should be 1. Uh-oh, something's wrong here. Oh, it's not y1. I've got it in y2. For some reason, I put it in y2, not y1. There we go. Now try it. That should give us an area of 1. Good. And if I go from 11 to 12, that's going to give me my answer to my first problem. And if I do my, to do the mean, remember that the mean of a distribution is the expected value of x. What is that? We take the x times the probability of x and we add them up. In this case, we add it up over the all x's that are possible and with respect to x here. So this is the notation we use here. In this particular one, all x's means only the ones that apply from 9 to 15. So in fact, this is our y1. And so basically you can just enter it in like this if you have the newer calculator that has the boxes here to fill in. On this one, we'll do it this way. So I can just say second enter, pull that up again. I said it's y1, it's actually y2 for me. And so where I've got my y2, I'm going to insert an x times y2. And I need to do it not from 11 to 12, got to do it over the whole thing, which is 9 to 15. 9 to 15. And enter. And oh, that's weird. Okay. Got these out of order somehow. There we go. y2 times x, or x times y2, and then do this. So this should produce the mean, which is 13. Now, it turns out that there's a shortcut for a triangular distribution. If you take the left endpoint, the right endpoint, and the median, and average those, you actually get the same thing. So that's 39 for the top divided by 3 is 13. Same answer. But this is the more general thing if I have any kind of formula. So either way we go, that's 13 for the mean. Now, to find the median, well, let's go to the variance next. The variance is sigma square, and that's the expected value of x minus mu square. So what we're doing is, again, adding up over all x's, in this case 9 to 15, x minus, well, the mu we just figured out was 13, and then this was y2 was our PDF, dx. Okay? So in general, this is integrate over all x's, add up over all x's, x minus mu square, PDF of x dx. Okay, so let's do that on the calculator. So I can go back to enter, and this place where I have an x this time, change it to insert a parentheses, x, insert minus 13, close parentheses, square. And this will give us the variance, which is 2. Now, we need to find the median. To find the median, we really need to have not the PDF, but the CDF. Okay? So I'm going to find the CDF of this one by basing it on Y1. So I'm going to go to Math 9, function, integrate. I'm going to go back to Y2 for my formula with respect to X. And then I'm going to go to the point where there's nothing below it, which is 9. And then go up to an arbitrary X. And so this will give me my PDF, hopefully. And the PDF should start at 0 and end up at 1 as we go on this window. So I can leave the left and right the same, but the Y max needs to go up to 1. And if I do this, it should go from corner to corner, 0 in this corner and 1 up in this corner for Y's. Well, not quite the corner because I moved it up just a little bit because I've got it going down to -1. So it starts at 0 here. Well, this is the PDF. Now the CDF is going to be next. It's going to start at 0 here. It's going to come up and go up to 1 up here. Now, this is using a lot of approximation techniques to come up with this, so this may be kind of slow, and sure enough it is, very slow, but nevertheless it is figuring it out for us. So let's just review. If you may have already have this set up in your calculator, you might have used different ones. So if Y1 is the PDF, then Y2 is Math 9, function integrate, Y1 with respect to X, and then you got to give it an A and an X. Now what you want is then plus the CDF of A. So if you can start at a place where this is 0 and use that A value there, that's going to be the best way to do it. And sure enough, this did start at 0 and end at 1, so that's a good news for us. Now the median is where we put 0.5 for the Y value on that curve. So it's again where we know the CDF. So if we're finding the median and we have the CDF, then we just want to know where the horizontal line 0.5 crosses at. So now I have 3 curves here. I've got to be a little bit careful when I do this. So calculate the intersection. Make sure I'm looking at the right curves. Y2 is not one of them. Up arrow. Y4, that's a good one. Hit enter. And then, no, not Y2. Y4, no. Y3, yes, that's one. Hit enter. And I want to, for my guess, especially since it's doing all this approximation, it's going to be better if we can go ahead and get this guy pretty close. I think I overshot it just a little bit. There we go. That's pretty close. And then hit enter. And it may take it just a little bit to compute because it's doing a lot of approximations here. Okay, and there we go. Okay, 13.2426. 4 decimal places, yeah. 13.2426. Alright, now we got some concept questions. Answer the following questions comparing and contrasting the CDF of discrete and continuous distributions. The graph of the cumulative density function, or CDF, is always 0 or approaches 0 on the extreme left for discrete. That's true for both discrete and continuous, which is the next question about continuous. That's true. Always 0 on the left. It is always 1 or approaches 1 on the extreme right. That's true here as well as here. The graph of the CDF for discrete is an increasing connected curve. Now, a series of horizontal line segments increasing in height from left to right, starting at 0 and 1. Yes, that's the best description. Let me see if I can show you a quick sketch of what one of those guys would look like. It's going to start at 0. Let's say this is the x-axis. You're going to start at 0. From some point on, it's 0. And then it jumps. Let's try it again. So here it's 0 up to some point, and then it jumps up, and it's horizontal for a while, and then it jumps up, horizontal for a while, jumps up, horizontal, maybe it jumps way up here, okay, but then eventually, from a certain point on, this is a y value of 1, and on the far left, this is a y value of 0. And so it's kind of a stair-step function. In fact, we call that a step function. So that's what the CDF looks like for discrete. Continuous CDF is going to start at 0 and somehow come up and level off or B1 at some point. This may actually be 0 here and B1 here, or it might just be an asymptote. So B there. For a continuous distribution, probability that x is less than a is seen as the y value above x equals a on the CDF. So if we have a CDF curve here, and here's the x-axis down here, okay, if we pick an a and we go up here, that y, that's a comma CDF of a, and CDF of a is the probability that x is less than a. So it's a cumulative probability. This is going to correspond to, let's say we got some curve like this, for example, and this area here, if this is the PDF, this area and this y value are the same if it's the same a. Okay. For a continuous distribution, probability of x is less than a is seen as the area between the PDF and the x-axis from negative infinity up to a. So that's what it is. So again, that's the second picture I showed you over here. That's this picture down here. The picture here corresponds with question number 7. Alright, same kinds of questions, but talking about the PDF this time. In both discrete and continuous probabilities, the output of the probability density function is always non-negative. It's always 0 or positive. The graph of the PDF of a discrete distribution is, it's a curve. It's probably some connected curve. The graph of the PDF of a continuous distribution is, I'm sorry, a curve for the continuous. It's going to be distinct vertical bars for the discrete case. Discrete case, a bar graph, frequency graph, basically. Well, like a relative frequency histogram, really. Okay. The height of the PDF graph for a discrete distribution is the probability associated with that input. That is correct. So if you have a PDF in the discrete case, you're going to have some bars here, whatever they might be. Okay. And the height of this bar here is the probability of that particular x value. Say this is a, probability of a is the height of that bar. Not necessarily its area. If its width's 1, it's its area. But it's proportional to that area. Okay? The height of the PDF graph for continuous distribution is not a probability. So when you're doing a continuous distribution, let's say maybe something like a normal distribution or something like that, the height here is not a probability. What are probabilities here? Areas. For a discrete distribution, areas between the top of the graph and PDF, the x-axis, are probability. That's false. They're proportional to areas. So if I say maybe added the area of 2 or 3 of these bars, then that area is proportional to it. What we're really doing is adding the heights. If we want to find the areas, then we need to take into account the widths as well. For a discrete distribution, areas between the top of the graph and the PDF and the x-axis are proportional to probabilities. That is true. They're proportional to it. For a continuous distribution, areas between the top of the graph and PDF are probabilities. That is true. On the graph like this, areas that you might see here are probabilities. So that's A and B. For the x, the probability that A is less than x is less than B is going to be some kind of shaded area like that. Let X be the amount of coffee distributed by a machine in fluid ounces. Assume that X is distributed uniformly from 7.7 to 9. Okay, so let's think about that real quickly. Uniform means we have a horizontal bar, and it goes from it's 0 below 7.7, and above 9 it's also 0, and in between it's a uniform height, a constant height. So what is that height? Well, let's look at what the base is. The base is 9 minus 7.7, that's 1.3, right? And we know that the base times the height is the area, but that area is 1, so the height is 1 over 1.3. In fact, why don't we just take that 1 divided by 1.3 and just store it as h. So now h is my height. And my equation is y equals, well, whatever that h was. And we can get rid of some things here. And so we're graphing that only from 7.7 to 9 for x. And so we got a nice little, and of course the area of that rectangle should be 1. Okay, so what's the probability that a particular cup will have less than 8.5 ounces? So that's from, well, technically negative infinity to 8.5, but there's nothing to the left of 7.7, so we're finding an area like this. Well, the width is 8.5 minus 7.7 for the width, and the height is still 1 divided by 1.3, so it's, well, it's, let's go back to here, it is 8.5 minus 7.7, that's the width, and the height is 1 over 1.3, so if we just divide that by 1.3, we will get the probability that we want, the area there. 2 decimal places, 0.62. Okay, between 8 and 8.1, very similar type of situation, a little bit different shading here, but we're going between 8 and 8.1, so that's 8.1 minus 8, and again we're multiplying by 1 over 1.3, so that's, well, it's just really 0.1 divided by 1.3, and that's 0.08. And the mean amount is going to be exactly right in the middle of that bar, which is halfway between 7.7 and 9, which is just averaging those two. 7.7 plus 9 divided by 2. And that is 8.35, and that's going to be our mu. 8.35, 2 decimal places. 8.35. Next. Okay. So 5 out of 9 done. Okay. Researchers at a university have designed, built, and tested a switch capacitor circuit for generating random signals. The circuit's trajectory was shown to be uniformly distributed on the interval 0, 1. Give the mean and variance of the circuit's trajectory, and then let's do some probabilities. Well, this is the same thing we just did because this is uniform. It's between 0 and 1, so the mean is halfway in between that, which is just 0.5. I'm averaging 0 and 1. The variance, okay, well, remember the variance is the expected value of x minus mu square. Now you may know a shortcut for a uniform, but if you don't know that, it doesn't matter. You can do x minus 0.5 square times the probability. Well, what is the probability? Well, if we're going between 0 and 1, it's going to have a height of 1 because that is the area we're computing. Here's an area of a square which must have an area of 1, 0 outside that. So the PDF formula, PDF of x is just 1 for between 0 and 1. So this is just times the PDF, which is 1. So in general we're doing x minus mu squared times PDF of x, and then adding that up over all x's dx. So this is going to be between 0 and 1, that. So we can do that over here. This is a function integrate over here. So math 9, okay, x minus 0.5 square times 1. Leave that off. It's always x next. That's like the dx right here. In the calculator, other version, you have to fill in the blanks here, 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 and here. And then the same numbers go in here, 0 and 1. They just go in this order here. And we get 0.083 repeating. By the way, as a fraction, that's exactly 1/12. Okay? And we want to round to 3 decimal places. Okay, so 0.083. Okay, now what's the probability that it's between 0.3 and 0.9? Well, what we're doing is finding this between 0.3 and 0.9. We're finding an area here like this, okay, which again has a height of 1, and 0.3 minus 0.9, 0.9 minus 0.3 I should say, is 0.6 is the base. Base times height is 0.6, so it's 0.6. Remember, areas of probabilities. Would you expect to observe a trajectory that exceeds 0.997? No, because that probability is very small. Very unlikely. And what is that probability equal to? Well, it's 0.003. Because remember, it's the area, again, from over here. We have our graph, and we're talking about a very, very thin sliver here that has a width of 0.003 and a height of 1, so that's a 0.003 for that. Next question. Psychology students at a university completed the Dental Anxiety Scale questionnaire. Scores on the scale range from 0, no anxiety, to 20, and extreme anxiety. The mean score was 12, and the standard deviation was 3.5. And assume it's normal with mu equals 12 and sigma equals 3.5. Okay? Find the z-score for a value of 18. Now remember, a z-score is your x value minus the mean, which was 12, and we're dividing by the standard deviation of 3.5. And that is, there's our z-score, round to 100th, 1.71. Find the probability that someone scores between 11 and 16. Well, this is a probability on a normal. We can find that by going to second variables, which is distribution, and normal probabilities we do number 2 when we're actually computing the probabilities, a CDF. And we just tell it the limits. We go from 11 to 16, and we give it the mean, which was 12, and the standard deviation, which is 3.5. Okay, about just a little under a half. 0.4 decimal places, 4859. Someone scores above 17. Okay, same command. Okay, this time we want to go from 17, and we want to go to infinity. Okay, instead of 16. Well, what can you put in for infinity? Well, you want to go. You can put in something really ridiculously large here if you want. Usually 10 standard deviations above the mean is plenty. So 10 times 3.5 is 35, and add that to 12, that's 47. So anything above 47, I'm just going to put 50. So anything 50 and above, that's going to 47 and above, that's going to be plenty good. If you want to put 100 or 1,000 there, you'll get the same thing. For example, let's try it again and put in, you'll see very little difference here if we make this 1,000, let's say. In fact, any difference is beyond how many decimal places we have there. So there we go. And round to 4 places. So that's 0.0766. Physical fitness of a patient is often measured by the maximum oxygen uptake. The mean of that is for cardiac patients who regularly participate in sports or exercise programs was 23.4 with a standard deviation here. Assume that this distribution is approximately normal. What's the probability that a patient in this category will have at least 20 on this scale? In other words, the probability that x is greater than 20. Well, it's a normal again. So we go to second variables for distribution. We want to find a probability, so number 2. And we want to go from 20 up. 20 up, well, to infinity. What are we going to put in for infinity here? Let me start with 100 and see if that may be too big or too little. Well, it can't be too big. It might be too big to be useful for us. And then let's go ahead and put in the mean, 23.4. and standard deviation of 6.30. Now, how far do I need to go up for infinity? Well, 10 standard deviations above the mean is a pretty good rough estimate. So if you go 63 and add to this, that's 63 plus 23, that's 86, 87. Anything bigger than that is probably going to be fine. So the 100 is going to be a pretty good for us here. And so what do we get here? 0.7053 to 4 places. What's the probability of a patient in this category has a maximum intake of 10.5 or lower? Okay, so again, same thing. This time we want to go to minus infinity. How about negative 100 for that? And we want to go from that up to 10.5. Do an insert here. Okay, and then of course the same mean and standard deviation, and there, that gives us our probability there. Now let's see what else we have here. We have they have an uptake of 10.5. Is it likely that they participate in this sports or exercise program? I'd say not likely, because there's only a 2% chance that they're this level or below. So not likely. Could happen. Small probability, could happen, 2%, but not likely. Question. Let's check. Well, I'll have to check this out and see here. Alright, down to our last question. The mass of a bearing manufactured in a factory is distributed normally with a mean of 20.12 grams and a standard deviation of 0.38 grams. Product specifications call for the bearing to have a mean mass of 20.14 grams within 0.1 gram. Give all your answers in decimal form rounded to 4 decimal places. So this particular question is dealing with a normal distribution, and we're going to be finding some probabilities related to that, and an inverse probability related to that, and then after we do that, then we're going to go down and look at some sampling distributions. We're going to look at the distribution of the sample means. So several parts of this question. Let's go ahead and get started in the first one. Now I'm going to save myself a little typing, I'm going to do a little bit of work with the calculator. 1, 2, and store it as M for the mean. Next, I'm going to take the standard deviation of 0.38 and store it as S. And that is the standard deviation of the individual items and the mean of the individual items, bearings in this case. And so the product specs have an upper and lower spec. So the 20.14 minus the 0.1, let's store that as L for a lower specification limit. L, there we go. 20.04, good. And the 20.14 plus 0.1 gram, let's store that as alpha U for upper. And a little bit of work setting this up at the beginning, but this will save me a little hassle typing all these things or trying to remember what they are and look them up again. So assuming I've got all these things entered in correctly, this will help. So what proportion in decimal form of the individual bearings are within specifications? That is between from the lower to the upper limits. Well, this is a normal distribution for our individuals, so we go to second VARS to distribution here. We choose number 2, a normal CDF. We give it the lower end, which is L, alpha L, and then the upper end, which is alpha U, and then we tell it the mean, which is M, and the standard deviation, which is S. And I know I've got all these things stored in the right places, so I can type those numbers in again. And we enter that, and it says to round off to 4 decimal places. So 2073. Pistons that are too large can be reworked, but pistons that are too small have to be scrapped and recycled. What proportion of the bearings are scrapped? Well, let me just put second enter and get that back. This time we want to go from minus infinity up to L. So this needs to be L right here, lower limit. And now we need to put in some appropriate number for minus infinity here. Usually you can go about 10 standard deviations below the mean, or a little further is fine. So 10 standard deviations would be 1. 0.1 times 10 is 1. So we need to go from 19 point something. You know, we can go from 19. I can go less. I can go from just from 0 will work. So there we go. And hit enter. And we get a value there. So notice I could have done the same thing and put in a different thing. For example, I mentioned 19 as one possibility. As long as I'm at least sort of 10 standard deviations below the mean. Actually 19 was not so good. Oh, I'm sorry. The standard deviation, 0.1 is not the standard deviation. The standard deviation is 0.38. 3.8 below this, or let's say 4 below it. Go down to around 16, it would have worked out. So if I go down, say 16, and compare this one at the top and this one here, and you see that they're the same. So anywhere in there is going to work as long as you're at least 10 standard deviations below the mean. That's going to be reasonable for minus infinity. At least in terms of how far it will go out to the calculator here. Now this next one, in number 3, we're given a percentage this time that the mass of the bearings are smaller than the particular value we're looking for. So in other words, we're given a cumulative probability. Well, that's exactly what an inverse normal, inverse cumulative distribution gives us. So an inverse normal, 0.99768, and then we give it the mean, which is just M, and the standard deviation, which is S, or I can type those in again, and this gives us the value there, and again I think 4 decimal places, so 21.1958. A random sample. Okay, so back up. an inverse norm there is when you have the cumulative probability, it'll give you the value of your random variable x in this case, which is in this case it's a weight or mass actually of a bearing. A random sample of 7 bearings is taken. The diameters are measured and then averaged. Since the individual piston masses are normally distributed, the distribution of the sample means are, well, exactly, if the original individuals are normal, exactly, then the all sample means, regardless of the sample size, will be distributed normally, and they'll have the same mean. So distributed normally with the same mean is correct. But they're going to have a smaller standard deviation. And so what we do is we take that standard deviation, S, try that again, alpha, there, okay, S, and we divide by the square root of the sample size. In this case, the sample size was 7. And I'm going to refer to this again. This is my new standard deviation for the sample means. Let's store it as, how about T? Okay, so T is my new standard deviation for the sample means. And of course, that's smaller than the 0.38. It's the 0.38 divided by the square root of 7. So, rounding that off, that's 0.1436. But again, I'm not going to use the rounded off version. I'm going to use this full decimals that I've got stored in the calculator. Now, what proportion of these average values are less than this particular number? So we want to go from minus infinity up to this and get a distribution. Well, this is again a normal distribution, so we go distribution here. We do a normal CDF, and we go from minus infinity. Again, 0 is going to be fine. And then we'll go up to our value, 20.3299. And then we want to give it our mean, which is M. And our standard deviation, which this standard deviation is the smaller one, which was T. There, and enter. And that gives us our number, 0.9281. And what proportion are within the specifications? So from upper to lower. So let's do this again. Actually, I can just do second entry, and we want to go from lower alpha L to upper alpha U, comma, the mean, which is M, and standard deviation, which is T, because it's the standard deviation of the averages, standard deviation of the X bars, and a little over half. So our original up here, only they weren't doing so well in this particular manufacturing situation, were they? Just about a little over 20% of the bearings were within the product specifications. They need some help on their factory. Okay, that's of the individuals. But notice, if you're just looking at the averages, much more of those are going to be within the product specifications. Okay, so notice if you were doing averages, sometimes when you're doing a manufacturing process like this, they'll keep track of the averages of a sample, say in this case a sample of size 7, and they'll see that well, nearly half of them are outside of product specifications. Well, that means it's even worse than that, because really that means that nearly 80% of them, of the individuals, are outside of product specifications. So that's kind of an interesting point there that we need to make sure we can get. So that gives us a quick review of this exam, and hopefully you can use this to help you study with for the final or retake, or just to study. Enjoy.